Alright guys, so what we're looking at today are some of the properties of exponents, rational, and just exponents in general. Our properties of exponents we have here. Now some of these we already know, you've worked with these before. So our product of powers, if we multiply like bases, a to the m times a to the n, we add the exponents. That's our product of powers. Now, power of a power, if we take something, a to the m to the n, the powers multiply together. Our power of a product is if we multiply two things together, a and b, and put them both to an exponent, we can put both of them individually to that exponent. Negative exponents, if we have a to the negative m is the same as 1 over a to the m. The reverse of this is also true. If we said we had 1 over a to the negative m, it's the same as a to the m, because we can move it from the numerator to the denominator or denominator to the numerator, and the exponent is going to change from positive to negative or negative to positive. Now, normally everyone's favorite a to the 0 is 1 as long as a is different from 0. Anything to the 0 power except for 0 is 1. Our quotient powers, if we divide 2 and the bases are the same, then we can subtract the exponents. And lastly, power of a quotient. If we have two things being divided to a power, we can apply the power to the numerator and denominator. And these here are all of our properties of powers. And we've done these before. Now, before we start actually solving or simplifying, we need to know if it is in simplest form. And the first one is no radicals can have perfect nth powers as factors other than 1. So if we can reduce the radicands, then we're going to. So we can't leave something as, say, the square root of 4, or 4 to the 1/2 power. Because if we can reduce it, we're going to need to reduce it. Because the square root of 4 is 2. 4 to the 1/2, well, that's the same as saying 2 squared to the 1/2, which is 2 to the 2/2, which is just 2. We can't, if we can simplify it, we're going to have to simplify it. No radicands can contain fractions. So inside the radicals, we cannot have a fraction inside of a radical. And lastly, no radicands or radicals can appear in the denominator of a fraction, in the bottom of a fraction. So no fractional exponents can be in the bottom of a fraction. So if we can reduce them, we're going to reduce them. Okay, so let's look at simplifying some of these here. Now the first one we have is 7 to the 1/4 times 7 to the 1/2. Now whenever we have like bases, so 7 and 7 are our bases, multiplying two like bases, we can add the exponents. So we're going to add 1/4 and 1/2 together. Now normally if we're doing these here, 1/4 plus 1/2, we need the bases to be the same before we can add them together. Or we can just use a calculator and add them together, and we get 3/4. So we have 7 to the 3/4. Now we do need to make sure this is in simplest form, so we don't have fractions inside radicals, or radicands. We can't reduce it any further than this here because 7 is a prime number. So this here is actually in simplest form. Now the next one we're looking at is 6 to the 1/2 times 4 to the 1/3, all to the second power. So we have a product of a power. And whenever we have a product of a power, we apply this power to both, and we multiply it. So we have 6 to the 1/2 times 2 times 4 to the 1/3 times 2. But with the 6, 1/2 times 2 is 1. So we just have 6 times 4. 1/3 times 2 is 2/3. Now in this one here, we don't have anything that will really simplify further than what we have already. The 4 can be rewritten as we could say 6 times, well, 4 is the same as 2 squared to the 2/3. And our 2 times 2/3 would be 2 to the 4/3, but nothing really reduces. So this here and this here are the exact same thing. They're just written in a different way. Yes? We do. Because 1/2 times 2 is? Yeah. Now the use of changing the 4 to 2 is if it would reduce in some way. Because if that base, the number in the bottom of that fractional exponent had been even and it would have reduced with that 2, then we would have wanted it to. But either one of these here would work. Any questions on A and B before we look at C? Now C, we can do the same thing. We can apply or multiply each of these exponents by -1/5. So we get 4 to the 5 times -1/5 times 3 to the 5th times -1/5. Well, with the 4, 5 times -1/5 is -1. Again, 5 times -1/5 is -1. Now, we can't leave an exponent negative. But to make an exponent positive, we move it from the numerator to the denominator, or denominator to the numerator. So we'll move both the 4 and 3 from the numerators to the denominators to make the exponents positive. Now, at this point here, we would be finished, but can we actually multiply the 4 and 3 together? Yeah, because there is no other exponents besides 1, and 4 times 3 is 12. Now there is a difference between this 4 and 3 and our 6 and 4 here, because in the previous, the 4 is to the 2/3 power, yes? We didn't write it out, but really this is saying that we have 6 times the cubed root of 4 squared. We have it inside that radical, so we can't really multiply those together. But since the 3 and 4 in part C are both to the first power, we can actually multiply them together. Questions on any of this here? Let's look at the next one, D and E. Now the issue we have with these here is that both of these are fractional. We have fractions. We cannot have radicals or fractional exponents in the bottom of a fraction. But for D, we do have like bases, yes? Whenever we have like bases, we can subtract the exponents. So the numerator's exponent is 1. The denominator's exponent is 1/3. So we can subtract them here. And well, 1 minus 1/3 is 2/3. And that is it. Now the way we subtract the exponents, it's always numerator goes first, denominator goes second. Now if it had been, instead of positive 2/3, if it had been negative 2/3, then we'd have to work it back out from there. Any questions on this here? Any questions on anything we've done so far? Okay. Let's look at E. Can we do the same property we just did with D with 42 and 6? Are they like bases? But is 42 divisible by 6? Yeah. Now, our quotient of a power property stated that if we have A over B to the M, it's the same as A to the M over B to the M, yes? And with this here, we can go in the other direction. We don't have to just apply the power. We can also pull the power away. Because if we look at the 42 and 6, they are both to what power? 1/3 to the second. So what we could say is that this is 42 over 6 to the 1/3 to the second. Is that we can pull the 1/3 away from the 42 and the 6. And the reason that this is helpful or nice is because what is 42 over 6? 7. 42 over 6 reduces to just 7. Now we can multiply the exponents together because the exponent with 7 is just 1. So we say 1 times 1/3 is 1/3, and 1/3 times 2 is 'So this one here, we pulled that 1/3 away from the 42 and 6, which simplified that fraction completely, and then we could go from there. And the main reason we did this is because 42 divided by 6 gave us a whole number of 7. Any questions on this here? Let's look at some more of these here. Now the next one we have 2 to the 3/4 times 2 to the 1/2. Since we have like bases, we're going to add the exponents. So we're going to take 3/4 plus 1/2. Again, we can do this in a calculator. 3/4 plus 1/2 and get 5/4. So we end up getting 2 to the 5/4. And that is it. Now we can look at the next one. 3 over 3 to the 1/4. Since the bases are the same, we can subtract the exponents. So we have 3 to the 1 minus 1/4. 1 minus 1/4. We can do it by hand or in a calculator. And either way, we will get 2 3/4. And that is as simplified as it gets. There's no common factors we can simplify out. It doesn't reduce any further than that there. Any questions on any of this here before we look at number 3? Now, number 3, the bases aren't the same. 20 and 5 are not like bases, but 20 over 5 is divisible, yes? We'd have it to the 1/2, yes. 20 over 5 will reduce to 4 to the 1/2 to the 3rd. Can we actually reduce 4 to the 1/2? Because the 1/2 power is the same as what? Is the same as the square root of 4. So we can look at it that way. Over. And what is the square root of 4? So we have 2 to the 3rd, which is 8. So some of this is knowing our perfect squares. Because what we could have said, gone a different way, is 4 is the same as 2 squared to the 1/2 to the 3rd. And if we multiply our exponents together, 2 times 1/2 is 1, times 3 is 3, which gives us 8. Now, all the other ones we've done for this year, 1 through 4, have been prime. 5 is prime. 7's prime. So they're prime. They can't reduce any further. But this one here worked out that it actually could. (20 to the 1/5, 1/2 over 5 to the 1/2, close parentheses, to the 3rd, and the calculator actually gave us 8. But it only works this way if it is a nice number. Because if we look at, say, the first one that we did, for this here, 2 to the 3/4 times 2 to the 1/2, 2 to the 3/4 times 2 to the 1/2, we're not going to get 2 to the 5/4. We're going to get 2.3784 this here. Now, if we put in 2 to the 5/4, we do get the exact same decimal. It just won't simplify it in this form. No. Because the 30xs will keep it in radical form and square root form. It doesn't like doing it with higher degree, higher than that, or in fractional exponents. Let's look at the next one here. So this one here, we're going to multiply both of our exponents by 3. So we have 5 to the 1/3 times 3 times 7 to the 1/4 times 3. For with the 5, 1/3 times 3 is 1. So we just have 5 times 7. For the 7, 1/4 times 3 is 3/4. And that's as simplified as it gets, because 5 is prime, 7's prime, so there's no way we can rewrite them with perfect squares, number times itself. And that's as simplified as it gets. We don't have any negative exponents. We don't have fractional exponents in the bottom of a fraction or fractional exponents in a radical. Questions on any of this here? Let's look at these here. So 3 to the 1/2 times 3 to the 3/2. Whenever we have like bases, we have the exponents. 1/2 plus 3/2 is 2. Can we leave it as 3 squared? Can we actually take 3 squared? What is 9? So we'll actually simplify this, because it does simplify to a nice number. Unlike 7 to the 3/4 is not going to be a nice number. It's going to be an ugly decimal, quote unquote ugly decimal. So we just leave it. Here we can actually simplify it.
So if it looks nice, we can do it?
Yeah, so 3 squared is nice. We can do it there. Where, especially in the calculator, 7 to the 3/4 gives us this here. We're going to leave it as 7 to the 3/4. We're not going to turn it into the decimal, unless it specifically asks us to round to the nearest 10th or 100th. Let's look at the next one. 7 to the 2/3 times 7 to the 1/2 would be 7 to the 2/3 plus 1/2. Two-thirds plus 1/2 is 7 to the 7/6. Yeah, it'd be nice if it was 3/2, because then it would work out to be 49, but questions on this here? I have a feeling we feel comfortable with these two here, yes? Powers of powers, division of powers we feel good with. (25 to the negative 1/2). This here, so 1/2 is the same as what? A square root, yes? 1/2 and square roots are the same. So can we take the square root of 25? 5. 5 times 5 is 25. So it does work out that we could plug 25 to the negative 1/2 in the calculator and get a nice number. Because to work this out, since We have to turn it into a fraction, which does give us 1 over 25 to the 1/2. Now we can't necessarily leave the fractional exponent in the bottom of the fraction, but I do know 25 is a perfect square. It is 5 squared. And our powers of powers multiply. So 2 times 1/2 is 1. So it just leaves us with 1/5. Twelve to the 1/6 over 3 to the 1/6 to the 4th. Well, the bases aren't the same, but since both the 12 and 3 are put to the same exponent, we can pull that exponent away from it. Now, we can only really do this if the exponents are the same. If the numerator had been, say, instead of 1/6 was 1/3, then we'd have to do some manipulating to be able to do this, because we can only pull it away if they are the same. But since they are, that leaves us with 12 over 3 inside. And 12 divided by 3 is 4 to the 1/6 to the 4th. Now we can multiply the 4 and 1/6 together, which gives us 4/6, or we could say 2/3, yes? Which gives us 4 to the 2/3. Now, probably looking at this and some of the ones we did before, because the last time we had 4 show up, we rewrote it as 2 squared, yes? But here, if we did that, I could say 2 squared to the 2/3, which gives us 2 to the 4/3. Did the fraction really reduce at all? No. So leaving it as 4 to the 2/3 or 2 to the 4/3, either one of them works. Now, if we go back to this here, when I reduced it to 2 squared, the 2 and the 1/2 actually simplified. They reduced. That's why we did it there. Because our 2 and 1/2 reduced gave us 3. Now, if doing this had caused the fraction to reduce, then yes. The reason I didn't do it originally is our denominator became 3, yes? Will 3 reduce by 2? No. So either one works. Questions on any of this here? Don't think we have too many more of these. 3 more. Now, looking at this one here, there's different ways we can go about this. One of them is we can multiply by our negative 1/3. And there's nothing wrong with that, because if we do this multiplication of negative 1/3, we'll get 4 to the negative 1 times 2 to the negative 1, because our 3 times negative 1/3 is negative 1. And the same thing for 2. Yes. Because I'll do both, because we could go and say that we have 1 over 4 times 2. Or I can say that I have 4 times 2 to the negative 1. Because this would give us 1/8. This here would give us 8 to the negative 1, which is 1/8. We still get to the same place, just one of them took us a step further. Just took one more step. Questions on this here?
So we could make the 8. No, it's a negative.
Yeah, the negative exponent. Now, okay. Back up. Now, with the negative exponent to begin with, we know we'll have to move it from the numerator to the denominator, yes? So I could have moved it from the beginning. We could have moved it all to the bottom and multiplied it out. And we are done. Yes.
I just typed this calculator because the exponents were the same.
Yeah.
So I just multiplied 4 and 2 and then typed that in and I got the same.
Yeah, and it works out because the radicals simplify. We don't have a fractional exponent left, do we? No, it's just 8. So the calculator can do this quite nicely. The ones that we don't, or it won't, are whenever we end up with something like one of these here, where we still have that fractional exponent left. Then it's going to want to approximate it. Okay, let's look at the next one. Now, before we get too far into this, 27 is a little interesting. Can we rewrite 27 as a number times itself? What number times itself a few times gives us 27? Because we know 3 times what?
Oh, yeah.
And 9 is? So 27 is what? 3 cubed. In the calculator, if I said 27 to the 1/3, we actually get 3. Now, looking at this here, 3 cubed to the 1/3 times 6 to the 1/4. Now, I don't do it with 6 because the only multiples or products of 6, factors of 6, are what? 2 and 3. We can't write it as a perfect square, or 27 is a perfect cube. Now, the main reason I bring it up is because 3 times 1/3 is 3. So if we can simplify, we want to simplify it. Now, one way we can check some of them is just plugging them into a calculator, 27 to the 1/3 reduced to 3. Now, we do have this here. So the last thing we need to do is distribute the 2, which would give us 3 squared times 6 to the 1/4 times 2. Well, 3 squared is 9. 1/4 times 2 is 1/2. And that's it there. Any questions on any of these here? We ready for the last one? We get this here. Will 18 and 9, our numerator and denominator, will those two numbers divide evenly? Yes. And if they do divide evenly, this is when we do pull it out. Pull the 1/4 back out. If they do divide evenly. If they don't, we'll look at that on Monday. We have to do something different. Now 18 divided by 9 is 2. Now, up to this point, we haven't done this, but can I still multiply the 3 1/4? Yeah, I mean, we could say that this is 3 1/4 and apply it there. Or we can say that this is to the 1/4 to the third, and if we multiply them together, we get 2 to the 3 fourths. Now, 2 is prime. There's no way we can rewrite it as a number to a power. So this is as far as it goes. And again, a lot of this is just manipulating these numbers to get them to look nicer. Questions on any of this here? And that is it. Yes.